I have a problem ending
If
earlier.
you stop later, I can make you break.
Okay, yeah, so I'm going to talk primarily about new results out this year on short-range correlations, the EMC effect, connection from between them, and from what I call EAC phase 0, and some people still call Jefferson Lab 12 GeV. So I'm going to focus primarily on things that relate to the EMC effect, because I think this really boils down to the essence of the EAC in terms of understanding scale separation and confinement in QCD. So I like to destroy this kid's fairy tale by thinking about it in terms of physics. So what we all learned in kindergarten is that when we have a weakly bound system in a strong external field, obviously that field will impact the structure of the system. But if we have a strongly bound system in a weak external field, that field should not impact the system. When we think about QCD, we have our quark piglets living in a very strong proton house, right? The mass of the proton comes from the interactions, as we know. Nuclear binding energy is about 8 MeV, 8 MeV GeV. Scales are separated, life is good. But we know from the EMC effect already 35 years ago that is not the case. Scales are not fully separated. And when you look at the ratio of the structure function of nucleons in iron compared to the neutron as the best proxy we have for a quasi-free proton-neutron pair, we see that when we expect to get some curve that is more or less flat and then going up because of Fermi motion, we get something that is not that. And from looking at the experimental references I put here, from the first one to the last one, 35 years, we're still measuring the effect. That tells you something about A, our understanding of its origin, and B, how interesting it is, because we're still trying to find out more and more about what is going on here. So typically people describe this in 3 regions, the shadowing and anti-shadowing region at low X, EMC region in the kind of valence region between 0.3 and 0.7, and Fermi motion region. My talk will ignore this part and talk about basically everything that's going on here in terms of short-range correlations. I think Mark will talk about what's going on down here, and we're very much interested in expanding the connection with short-range down there as well. So the way we think, the physics we think drives a lot of the EMC effect is coming from short-range correlations, these pairs of nucleons that are very close together inside the nucleus. And so what I'm going to do today is I'm going to talk about how short-range interactions manifest themselves and impact our understanding of nuclear systems across resolutions, from how short-range interactions affect properties of many body systems, so basically the nucleus as a whole, focusing on neutron-rich nuclei, then talk about the fundamental essence of the short-distance part of the NN interaction, which really have not been probed too well so far, and then zooming in and looking at nuclear substructure for short-range correlated or strongly interacting nucleon pairs. And this is going to be based all on new data. So the first thing I'm going to do is present you with the new data. And so we have a Nature paper and a PRL that came out just recently, a paper on the archive from last week, another one on the archive whenever I get 3 minutes to upload it, and 2 more that are not on the archive that I'll show you results from because they're done, they're just not on the archive. And once we go through all this data in a coherent way and try to make it as painless as possible, I'll show you how, from this data, we see the picture of short-range correlation serving as a bridge between nuclear structure and quark-gluon dynamics, which is part of what we want to study at the EAC, but we already have a lot of information coming up from JLab 12 GeV, as again, I like to call it EAC phase 0. So, EMC effect, 35 years after discovery, well over 1,000 papers, still no conclusion on the underlying cause. But we have lots of data, and data can guide us as to what is actually going on, and data, as we all know, can also kill theories or bring up or inspire new theories. If you look at the most extensive data sets we have on the EMC effect, here I show you the stack measurements from 94, going on through a bunch of nuclei, and our most recent measurements from Jefferson Lab, which focus on heavier nuclei from carbon all the way up to lead with extremely high precision. And what we see is that in this region of the EMC effect, always we see this universal linear decrease in the cross-section ratio. For the JLab data, you can see, I mean, this is as linear as it gets. You really don't have any freedom to fit anything that's non-linear here. But what we do see is that the slope or how low we go depends on A. So it is a nuclear effect in terms that when you look at helium-4, for example, and you reach up to about a 10%-ish effect, but when you go all the way up to gold or lead, you're already at a 20% effect. So obviously, by making the nucleus bigger, okay, making nucleons more tightly bound, more interacting.
Sorry, but the minimum seems to be pretty stable, right? It's always around 0.75 or so, the minimum.
No, here it's at 0.9.
Oh, come on. Look at the hour bars. Look at the hour.
The X-man, the exposition.
The exposition?
The exposition.
Yeah, 0.7, yeah, always. From 0.3 to 0.7, as stable as they come. We have fits, we have all these plots of, not a bit here, but we have all these plots that we did of where you cross from one and where is the minimum, as flat as they come. But how low you go on the y-axis, that changes a lot. Okay, and definitely the x. But
when you divide this way, heavy nuclei, difference proton neutron becomes.
yeah, I'll talk about this isoscalar correction later. Yes, I'll get to that. Anyway, so it is a nuclear effect in terms of how the slope of the decrease really depends on A. So something in the nuclear dynamics is driving it. So we need to look at the nucleus and see what can we learn by looking at the difference between different nuclei to try to understand the EMC effect. So when we consider the momentum distribution of nucleons in the nucleus, we have the standard mean field approximation leading to a shell model, Nobel Prizes, etc. And that means that you basically have nucleons populating different shells, different orbitals, occupying momentum states up to some Fermi momentum, and that's about it. But we know that there are correlations in the nucleus, and we know from measurements and ab initio calculations that they populate this continuum of high momentum states above the Fermi momentum. And we also know that theoretically reconciling the existence of such a high momentum tail within a mean field approach is very challenging. Very challenging, I mean, it cannot be done. So you have to have two separate kind of descriptions if you want to work in effective theory for the nucleus. You have a mean field part describing what is going on up to the Fermi momentum, but that mean field is depleted in terms that it doesn't tell you what is going on with all the nucleons in the nucleus, it only captures some of them. So above K Fermi, there has to be some other physics describing the remaining nucleons shifted from here to here, creating this high momentum tail. And from electron scattering experiments, we really understand that there is, in fact, a difference in the microscopic description of the physics here. Here, we basically have what people know as quantitative factors. We have a single nucleon being very well described by the interaction of, effective interaction of an A-1 system, basically, again, populating shells, collective motion, etc. And here, it is no longer a single nucleon. Description is no longer valid. We have nucleon pairs that are strongly interacting. And actually, the interaction with the residual A-2 system is quite weak and is not the most significant part. Actually, their interaction here that dominates, well, here it's the interaction of the single nucleon with the residual system. So to become a bit more concrete on what we're talking about, again, these pairs of nucleons that are close together, the operational definition we have for those guys are pairs of nucleons that have high back-to-back relative momentum and low center of mass momentum. We always talk about high and low is relative to the Fermi momentum of the nucleus as a scale. So this is the definition that I will follow throughout my talk. There's lots of data coming out of the JLab data mining. I just want you to know about it. I'm not going to bore you with all of it. You can read the papers. I will tell you about the main results that are relevant for us today. So the way we study correlations, there are a few ways to do it. Our group uses what we call hard knockout reactions. So we come in with a probe, okay, and the probe needs to be very high energy, it needs to have the resolution to actually separate out nucleons in the pair, so a few GeVs, and we exchange, in case of electron scattering, virtual photon, knocking out a single nucleon out of the nucleus. By knowing the instant electron and measuring both the scattered and knocked out proton, we can reconstruct the initial momentum of this nucleon. And now if I had a pair of strongly interacting nucleons with very high relative momentum and I did a very hard, fast knockout, basically fast removal of one of them, the other one has to recoil out of the nucleus. This is a very fast process. The system does not have time to rearrange itself, to account for all this momentum that this nucleon has, that nothing is balancing it anymore. So it has to recoil out of the nucleus.
This is strongly you can pair more or less at rest.
Yes, low center of mass. Talking only about low center of mass, yes.
So
Yeah.
you put 3 nuclear configurations.
Yeah, I'm not
Doesn't work.
completely not talking about that, I agree. But in this, what I'm talking about here is the spells that I define.
Important point because
Yeah, for the pairs
discussed
that,
it, but there is the different protons.
yeah, and for the pairs that I define 2 nucleons, high back-to-back relative momentum, low center of mass momentum, this is our problem. You want to probe other objects, different considerations coming. So again, break up, detect both nucleons, and then you can reconstruct the initial state inside the pair. The problem is that this is a very nice and pictorial view of things, and it means that we're talking about this very clean breakup diagram. You have a correlated pair, you interact with one of the nucleons, you knock it out, the other recoil, and life are very nice, full of teddy bears and unicorns. In reality, the same final state could come from other reaction mechanisms. So there could be other things going on in these diagrams that will lead to the exact same final state. As an experimentalist, obviously I'm blind, we're all blind to what is going on inside the nucleus. We know what came in, we know what came out, and any valid diagram that comes in between has to be summed coherently. A lot of work was done by Frankfurt-Strickmann and others about understanding these kinematics and really finding ways to isolate the short-range diagram compared to the others. And the magic numbers, the magic words that we have are high Q square, X greater than 1 kinematics. Okay, and again, I can give a whole seminar about why those kinematics, but lots of calculations and measurements showing that these things work to suppress isobar excitations, the meso exchange current. And the considerations, the general ones, are quite simple. Meso exchange currents are suppressed like 1 over Q square compared to the short range diagrams, so higher Q square, the more they are suppressed. And when you go to X beyond greater than 1, that means that you're putting in more momentum than energy with your virtual photon, right? It's Q square over omega, basically. And that means that the probability of exciting the nucleon goes down. You have data to support that. Final state interaction you can never kill, but you can calculate them because at high Q square, nucleons have very high momentum above a GeV. So you can actually use the Glauber, general Glauber theory to describe them. And again, I won't show you the details of the calculations to show that they work. That's much better, right? So here you see data compared to a zero range approximation calculation, and then compared to one that includes the relativistic multiple scattering Glauber approximation. No tuning of the Glauber parameters here, all taken from NN, and you can see how well it works. Here again, these black data points are knockout of nucleons from short-range correlated pairs. These dashed lines here come from Frankfurt-Strickmann and Jalov, or from a calculation by Vijay Panda and others, all done well before this data was even taken, and you can judge the agreement for yourself. In the most recent work we did, that's the one that will be on the archive once I have some time to put it on there, we looked at transparency ratios for knocking out protons or neutrons, either in mean field or short-range kinematics, so basically doing everything we can with nuclear knockout, comparing to 3 different types of Glauber calculations. And you can see the agreement of all 4 reactions with the Glauber predictions, and so not post-predictions, all predictions, well outdating the data. And we can see that actually the attenuation of the cross-section ratio goes roughly as A to the 1/3, indicating a surface-dominated process as one would expect. So we have this reaction, and we have a reaction theory that we think is good, and we understand what's going on, so we can start looking at data. So this is how short-range correlation breakup events look like. So if you have a 4-pi detector and you look at it from the side, this is the momentum transfer vector. So this is the kick I give the nucleons. This is the initial, reconstruct the initial momentum of the nucleon I knock out, and this is the partner nucleon. And we can already see that these nucleons we reconstruct are really back-to-back already in the lab frame, or the momentum transfer data. Reconstructed momentum vectors that we measured.
And how many events? Such as many hundreds?
A few hundreds here, and I think about 50 or 100 here. And you can see that really this correlation, back-to-back correlation, you see it clearly from carbon all the way up to lead. So this is nice, but when we want to quantify things a bit better, so we want to know how clean the breakup process is, and the answer is very clean. So when you knock out this pair and you look at the residual system, in the case of helium-4, you know it has to be a 2 nucleon with low excitation. Signal plus background is black, red is the off-time background, and you can see that the excess above background is clearly at either the deuteron in the case of PN or 2 neutron mass in the case of NN. So we see clearly very low excitation residual system. So basically we have this strongly interacting pair and a very weakly interacting low momentum residual
How big
system.
are the momenta we are talking about? How big are the momenta we are talking about?
For the nucleons that we knocked out, well, the leading nucleon has momentum of about 1.5 to 2 GeV because that's the one that's absorbing the momentum transfer and with IQ square. The recoil is anywhere between 300 and in this case up to 800 MeV/s. So just above K Fermi, standing up.
So these two nucleons move together to space large moment.
They have low center of mass momentum, high relative momentum. But this residual system has a low center of mass momentum.
How
Sigma of 100, it's a Gaussian with a sigma of 100 MeV/s. I'll show it to you in a few slides. This is from the Corval data.
no, I know.
You're not knocking out a pair, you're knocking out one nucleon with a fast.
Yeah, there's a
perspective.
exactly. There's a very big difference between the momentum of the knocked out nucleon and the recoil. The knocked out one goes in the Q vector direction with momentum well above a GeV. The other one is a fast recoil, in the sense that it's above K Fermi, okay, but it's still well below a GeV.
What happens to the nucleus? To the rest of the nucleus?
That's what the missing mass is.
That's what the missing mass is. Those are the two other nucleons, and they are basically spectators. And I'll show you more measurements at heavier nuclei of what is the system, the A-2 system. Then there was this plot that I think many of you have seen by now, a science paper in 2008, receiving a lot of papers in PRL that came before that. Basically from electron knockout, and we can do the same thing. It was done with protons as well at Brookhaven before JLab, and this is the point here. And what we see are two things. One, in the momentum range of 3 to 600 MeV/s, so just above K Fermi, up to 600 MeV/s, within statistical accuracy of about 10%, whenever a proton was knocked out, there was a partner recoiling out, period. We did not see anything else coming out. We did not see cases where nothing came out. Within, again, this statistical accuracy. More surprising, whenever we knocked out a proton, almost always, meaning a ratio of 1 to 20, we got a neutron recoiling out. So it wasn't just a factor of 4 from Wigner counting spin, isospin that you would normally get for pairing interactions for NP having a bit more states. No, it's a factor of 20 more NP than PP pairs clearly observed in this knockout event. That's one of the big surprises that made this thing go into science. People have explanations for that in terms of tensor interactions, and we wanted to see if this continues all the way in heavy nuclei. There was a science paper in 2014 expanding those measurements all the way up to lead, observing again that the NP fraction dominates, but there was a caveat here. What we did in this work, we did not really measure neutrons, so it's tough to do. We measured for each proton we knock out, what is the probability of getting another proton to come out, so that for carbon we got consistent results, and so that basically we don't have many recoiling protons, so whatever we don't see is associated with proton-neutron pair breakup. Now, this was very clearly stated, and there are good reasons to believe this assumption is correct, but the best thing to do to know that it's correct is to actually test it. So new data is coming. So this is a paper that was put on the archive a few weeks ago, this is a video now, where we actually did the full thing. We knocked out either protons or neutrons and detected the recoil proton. So a bit different. Before we used to knock out the proton and look for recoil proton or neutron. Now we switch it. We knock out protons or neutrons and look for recoil protons. And again, all these technical experimental details should lead to the same experimental result, and that is what you see here. So these are the cross-section ratio for knocking out a proton-neutron compared to a proton-proton pair. We can put a bound that proton-proton pairs are about 6%, but then there could be single charge exchange corrections that will basically feed PP states. So if we have lots of NP pairs, let's look at extreme case, you have only NP pairs, you will still measure experimentally some PP knockout because of a neutron doing single charge exchange on its way out of the nucleus. We can correct for that in a model-dependent way, and that's the data after the correction with the uncertainty. But we know that the correction can only lower the ratio and not pull it up, and that's why we can safely say there's a bound of about 6%, and depending on how well you believe the single charge exchange corrections, I think you should, can go down to about 3 or 4%. So NP dominance throughout the nuclear chart is now actually well established. So this tells us, going back to our diagram of the nucleus, that we do have this NP pairs coming in here. And I told you that this is understood to be a result of a tensor force, tensor interaction proportional to the spin. So you need a spin one state. You try to take two protons, put them in the same place with the same spin. You either get a slap from Pauli or a Nobel Prize, probably the former. So NP pairs are what's dominant here. But now we can really ask ourselves, can we probe the actual interaction that is driving this NP dominance? And there's a problem doing that with electron scattering. We know that electron scattering is a very successful tool for many things. Probing the NN interaction, to be honest, is not really one. Wherever you try to look at momentum distributions, reduced cross-section, anything you do at very high momentum, you always see these logarithmic reaction effects from plane wave to the data that are there, and it's very hard to avoid it. So this is this data. It's basically a reduced cross-section ratio. Sorry. These are reduced cross-sections for helium-3. So you knock out the proton, and you look at the reduced cross-section. That's supposed to be proportional to the momentum density or the spectral function. And you compare that to a calculated cross-section either in a plane wave or with single scattering or full finite state interaction model. And you see that the data and the model... It's momentum, it's a missing momentum. It's the reconstructed initial momentum of the nucleon you knocked out. So you do E prime P, and you reconstruct the initial momentum of the knocked out nucleon. So what you detect minus the Q vector. And that's the standard thing people do, and it just works up to about K Fermi and always fares above that. An easy way to see it is here. So again, a reduced cross-section for either knocking out a proton from helium-4, leaving the residual is a bound neutron, so a two-body breakup, or a three-body continuum breakup. You remove a proton and you have an unbound NP pair left behind. And you can look at the reduced cross-section as a function of the reconstructed initial momentum of the guy you knocked out. Again, things work quite well up to K Fermi, up to about 300 MeV per C, and then reaction mechanisms are basically logarithmic. Here you can see it again in a different way. You look for a given missing momentum as a function of the missing energy, plane wave, full calculation compared to data. So we've always been dominated by reaction mechanisms that are at high missing momenta, which did not let us really probe the wave function in that region. So we always have to integrate over here and do some overall corrections to extract information. But as you can see here, actually, these final state calculations, interaction calculations, are doing a good job moving us from the plane wave to the data. And again, these are parameterless free calculations with enough measurements that things are constrained well enough that people can do these calculations as predictions and not as post-dictions trying to explain the data afterwards. And these are calculations by Chofi Dignati and Maximilian Albioli and others. So what Misak did was he took this reaction theory, again, based on Glauber, etc., and he tried to see, well, if you look at the full cross-section compared to a plane wave impulse approximation, the two are as close to one as possible for different values of missing momentum as a function of a kinematical variable describing the angle between the momentum transfer and the nucleon you're interacting with. So finding kinematics where things are suppressed, and there is actually a kinematics of either parallel or anti-parallel momentum orientation. So this is the Q vector. If we're either parallel to it or anti-parallel to it with the nucleon that we're interacting with, finite state interactions are suppressed. If you go to perpendicular kinematics, like the previous data, what we call X of 1, quasi-elastic scattering, things are high, and you can see as you go up in missing momentum, they become worse and worse. So people did measurements in this magic kinematics, and this is knocking out a proton from the neutron. And again, you can see that at angles where the rescattering is large, again, the plane wave does not agree with the data. But as you go to better and better kinematics, the difference between full calculations and plane wave and the data becomes smaller and smaller. And if you take ratios of two similar nuclei, similar mass nuclei, and you work again at high Q square, where the PT and NN cross sections are very similar in the Glauber, which is what we put into the Glauber, there's really no difference in cross section ratios between a PWAA and a full calculation. So you can tell me here there are still 10–20% effect. Sure. Here they are gone. So that's what we did. This is a paper that is being drafted now, measurements. We took the data in April this year, and already Ray managed to finish his analysis, write the paper, will be sent to the collaboration in about a week or so. So what we did was we did proton knockout out of helium-3 and Triton to look for the isospin dependence of the short-range part of the NN interaction. Here you can see, for example, a PWIA simulation compared to our data for the missing energy in this two-body breakup from tritium, momentum transfers that are quite high, and most importantly, the cross-section ratio as a function of missing momentum. So here you can see our data in two kinematical settings. These are spectral function calculations that were ran through our acceptance and compared with the data, the dashed lines. These are momentum density calculations coming from quantum Monte Carlo, either using the INT-18 potential or high cutoff chiral perturbation based potentials, and you can see quite good agreement with our data. You can see sort of very interesting dynamics here, because if you consider helium-3 and Triton, you'd say, okay, we're doing proton knockout out of both of them, well, there are two protons here, one proton there, so the ratio needs to be 2. But I just told you that at high momentum, it's all NP pairs, so the ratio has to go down to 1. So we have to start at 2 and go down to 1, but we have to conserve momentum somehow, right? So if I shift nucleons here to 1, I have to go above 2, actually, at low momentum. And this is what we see. We see a clear transition from single body type approximation where ratio is above 2, all the way down to something that's getting around 2. And here the data seems to actually start going a bit up, but within statistical uncertainties, it's hard to say if we actually see a problem with any interaction or not. But this is the first time where we can actually do a direct comparison of data with plane wave calculations and get something that does not require corrections on our algorithmic scale. Okay, so we are really very excited about, first of all, the results as they stand, and what they show us that we have gotten to in electron scattering. It shows us that we are becoming mature enough to get to a point where we understand reactions well enough, we can trust calculations by Misak and others that have been constrained by enough previous data that we can do these PWIA comparisons to quantum Monte Carlo calculations and get results that actually make sense and are not crazy. And so we're very excited about that one. And that makes us be even maybe too cocky and looking at things all the way up to missing momenta of a GeV. So what you see here are initial results from, again, knocking out a proton and seeing how many times this proton is balanced by a correlated partner proton recoiling out. We start from just above the Fermi momentum and go all the way up to a GeV. And again, I told you we're supposed to be NP dominant in the tensor region, around 300 MeV per C, and really we do not hardly see any recoiling protons. But as we go up in missing momentum, as we extend out from what's supposed to be a tensor dominant region to a repulsive core that's supposed to be scalar, we see an increase in the number of short-range correlated pairs, and those match quite well our event generators that are using as input these quantum Monte Carlo wave functions with single charge exchange probabilities. All, again, nothing is tuned to the data. So we see from the data alone a clear spin-dependent moving to a spin-independent region of the interaction. So very small number of pp to very high number of pp. The shape is captured very well by this blue calculation, which if we scale by 1.3, which is some of the uncertainty we have to put in this calculation, it actually matches the data perfectly. And this is by Axel Schmidt, who will hopefully finalize it soon. But again, PWIA comparisons going all the way up to the repulsive core, seeing quite, in my mind, a remarkable agreement. So,
what are cuts on the momenta of the pair?
There are no cuts on the momenta of the pair. I'll show you from the same data how the momenta of the pair looks like in this slide. Okay? It's an excellent question. So, I've shown you that there are NP pairs, right, and that we can really start probing the interaction between them. Now, what about the interaction with the residual system? What happens to the rest of the nucleus? Well, this is the reconstructed center of mass motion of the pair, how the pair moves as a whole in the influence of the A-2 system. It is a Gaussian. Everything in the midfield picture should be. You look at one of the two components, it's a Gaussian started at 0. And we characterize these Gaussians by the widths. And if you look at the widths as a function of A, these are some old data from proton knockout, electron knockout, and the new data that we published in PRL a few months ago. And you can clearly see saturation of the center of mass motion that is consistent with either mean field calculations by Cioffi-Degliatti or Jan Rickabusch, or even by what you would get by taking two random nucleons and looking at how they move within a Fermi gas. Okay, it's at that level. If you take a pair of nucleons in a Fermi gas and you ask how does that move in the influence of the rest of the system, you get this line that magically goes fluctuate between our data points. So what we see is that these pairs indeed have throughout the map low center of mass momentum. And this thing, the fact that it saturates here is also very significant to understand the reactions, because when we go from carbon to lead, I would expect that if we're sensitive to much more of smaller scattering and not surface dominated, etc., I would see this thing blow up, and I don't. It saturates. So we're happy.
Okay, right.
Yes.
Follow up Mark's earlier question. In this kind of a theoretical framework, you have to have free body forces to get the right saturation in nuclear matter. Have any of these people attempted to say where their curves would go if you included?
So these calculations are effective calculations. These are shell model calculations for the A-2 system. So there are 3 nucleon for those do not have an fundamental NN. The quantum Monte Carlo that I'm comparing to here and in the other plot, those do have free body forces, and the effect of free body forces is significant here and significant like here. Okay, but not in this region.
Well, you move very fast and some things are missed. What they calculate is two body momentum, double momentum density, which is not the quantity which is measured. Basically, in some limit when you pick up pair small relative momentum, you may try to connect. But as soon as we have more complicated interaction with this residual system, there are corrections which is far from anything what was calculated. This is just mathematically different. So it's very natural that for some reason they are approximately coincide.
This is correct, but with a small caveat. We are not comparing to the two-body momentum densities they calculate because they have nothing to do with the measurement. So I agree with you that those quantities have nothing to do with what being measured, or very hard to correct what being measured, but we're not comparing to those whatsoever.
Quantum Monte Carlo calculate only.
No, one-body momentum densities are what they use. I don't use the two-body momentum densities they calculate because those are very hard to relate to what we measure.
It's even less directly connected.
I strongly disagree. We published all this work on the contact, and we've shown that if you analyze these things carefully, and I agree with you that there are caveats, but if you analyze these things carefully and you understand where you have what they call the real correlated nucleons and the long-range correlated that are not coupled, you can reconstruct the data fully. So I think there are lots of caveats and it's very detailed, but we have a spectral function. We published a spectral function 2 months ago.
Let's leave that for the
Coming from the decay function. Okay, so asymmetric nuclei. We want to ask what's going on as you add more neutrons to the system. Are still NP dominant? What do the neutrons do to the protons, vice versa? Insane analysis done by Mital Duer, really one of the toughest ones I've ever seen done at JLab, because she had to not only do the standard electron-proton knockout, which is easy, she had to do electron-neutron knockout. Now the problem with neutron knockout is that you need a neutron detector. And in class, there is no neutron detector. There's an electromagnetic calorimeter that neutrons are a background to it, okay? But she managed to struggle in the background, so she basically looked at when you knock out a proton, bends, and you can track it and do everything with it. Neutrons just have a spark happening in the calorimeter with very poor time of flight resolution. Nevertheless, she did a very hard analysis that was published in Nature about a month ago. And what she did, the first thing was, we said, let's see how many neutrons I have at this low momentum region below K Fermi compared to how many protons I have here. And let's see what's the ratio of protons to neutrons at the high momentum region. So it's an experimental neutron knockout cross-section divided by the elementary electron-neutron cross-section that you get from form factors. Again, divided by the experimental proton knockout cross-section divided by elementary electron-proton cross-section. You start by looking at carbons, asymmetric nucleus, the ratio of protons to neutrons better D1, no matter where you look, and that is what you see. mean field region, short range region, dim uncertainties, ratio of 1. You continue looking at the mean field region, there the shell model works and we know what's going on, and we think we should scale as n over z, basically. So as you add more neutrons, you should see more neutrons in low momentum, and that is what we see again within statistical uncertainty. This is not a fit to the data, this is just the n over z line, and we fit. That's nice. As we change our cuts and look at the high momentum region, however, the ratio of protons to neutron is 1, irrespectively of how many extra neutrons I have in the system. So I throw in more and more and more neutrons, and I still see here the same number of protons and neutrons as I would expect from NP dominance.
What is the value of third dimension?
About 250. It doesn't really change by much, and maybe by 20 MeV between carbon to lead. It's really, nuclear density is saturated, so it doesn't change much. So now we can ask ourselves, okay, so we added all these extra neutrons, right? And we don't see anything changing. So what happens with these outer neutrons? So let's take an extreme picture, right? We have a symmetric core and some neutrons in an external orbit. What do these neutrons here do? Do they don't correlate at all? Correlate only within each other? Or do they reach inside and correlate with the proton? Now, think about reaching inside in a nucleus is not really reaching inside, right? The neutron skin is extremely small. Everything is one on top of each other. So could be that this is the case. And I'm saying it could be because it is. So here what you can see is the fraction of high momentum protons in nuclei relative to carbon, or the fraction of high momentum neutrons in the same nuclei relative to carbon. So I'm asking myself, what is the probability of a proton to be at high momentum in different nuclei compared to carbon as a symmetric reference? And we see that as we add more neutrons, as we go to more neutron-rich nuclei, the fraction of correlated protons grows, but the fraction of correlated neutrons is either flat or maybe one side increasing, but it's basically saturated. So by adding more neutrons to the system, I'm actually making the protons more correlated. The first and last neutrons seem to have the same correlation probability of about 20%, but they correlate with the protons, and look at the numbers here. It's not a tiny effect, it's a 50% effect. So if in carbon I have, let's say, 20% of the protons, 20% of the neutrons in short-range correlated state, when I go to lead, it's 20% of the neutrons, but now it's 30% of the protons. So the proton correlation probability goes up by about 40 to 50%. So these are not small effects, they're quite big effects. Another way of looking at it. Last but not least, I just need it for the EMC stuff, so I'll just give you the bottom line. When we go to very high X in inclusive electron scattering, just E prime, we see that the cross-sections basically, so cross-section ratios of heavy to light nuclei basically saturate. And that's an indication that in these kinematics, you're probing correlations. I don't want to go into the details, I just want to say one thing. While we see these high X scaling plateaus that many of you might know in light nuclei, in heavy nuclei, you can judge for yourself if this putting a straight line here makes any sense. So we didn't feel comfortable with the scaling, so we went out and we remeasured it, work by Barak Schmuckler, and we do see scaling. So basically, the inclusive electron scattering cross-section has a very clear dynamics to it. There's a Fermi motion region, there's a dip, it goes up, until it reaches a threshold of about 1.45. Let's see with the beginning we have a very clear threshold, and then it basically becomes flat as a function of X.
What's the difference?
Q square is a bit different. We looked at that, and there's no difference. That doesn't cause it. They somewhat underbinned their data. If you look at the uncertainties here, right? They have enough data to put 3 or 4 times more bins like we did, and they chose not to do it. So I don't fully understand why they did it. And they are using small acceptance spectrometers, and in high X, it's actually, even though they have high resolution, at high X, it's very hard to work with small acceptance spectrometers because slight variation in understanding of your acceptance really affect things a lot. And when you have extended targets that you compare to, so this is foils compared to extended target, this becomes much harder. What we did was we did a simultaneous measurement where we had in the beamline at the same time a neutron target and a heavy nucleus. So we measured things at the same time to do a high precision comparison. And we used a large acceptance detector that allows to integrate over a wider part of the phase space to understand things better. So
actually, it's very useful to put also one line, extra line in this plot. When the invariant tangent in the Newton becomes closed, very close. So basically, the last couple of points, I don't know exactly this way, but last few points correspond to 15 million. So
Well, you should know because you're on this paper. But regardless of that, we do not include the last points in the fit, and we do not include those because that is where the Neutron cross-section basically drops in the kinematical cutoff effects of 2, right? So the Neutron cross-section falls off to 0 basically. They also do not include, if you look at what happens here, they also do not include the last point in the fit.
we know from first measurement which we did that for some reasons it's pretty much flat even where it should be. That's,
Yeah, I don't know.
but still, it's useful to.
You can put that.
Are you sure about this straight line? I can as well fit a slope like before.
Yeah, so if you fit a slope, what happens is that you get, we'll play the game. You will get a small slope, okay? But within uncertainty, the slope coefficient will be 0. So, I cannot tell you that here, I can tell you for a fact that this thing has a much better chi-square than this one, okay? And there is no question about this slope coefficient being non-zero, okay? Here, the chi-square is 1. If you fit a slope, you add another degree of freedom, the chi-square becomes much smaller than 1. So you're not really seeing any improvement in the qualitative description or quantitative description of the data. And the slope coefficient, sure, you'll get a slope, it will come a bit lower here and a bit higher here. But you won't
But the
get
points above 1.6 are systematically above them, right?
It's hard to say. So here we have 2 points above the line, okay?
3.
Which 2? This one is not included.
No, the next one is.
No, I'm saying, so here we have 2. Here we don't have any. Here we have 2,
Hold on.
and here we have a few below, a few on top. Again, it's very hard to say. This one is probably the one, not probably, this one is the one that can, let's say, entertain the best slope if you want. This one definitely cannot. This one barely.
So you leave the last point always out.
Yes, always out. And that's for, it has nothing to do with that, has to do with the fact that it's different physics happening there. That we know. And, some people would always tell you that we need to even take the second to last point out. For the fit, it won't change anything because those have large uncertainties. Like Mark said, it could be that it would be best to actually exclude also this second to last point as well. Because again, the Neutron cross-section starts falling, and that will immediately introduce an increase in the cross-section ratio. We know that. Okay, so we have 2 regions in the momentum density, and we see that when you go to neutron-rich nuclei, because of these NP region correlations, protons become more correlated than neutrons. Now let's get to the essence of things, EMC effect. So how does all of this relate to a protonic picture? Well, again, I showed you that we did these measurements of both SRC, but also EMC effect, and we did it with extremely high precision. Okay, if you zoom in, you can compare the stat data to ours, and it's not that we did not plot the uncertainties, they're just smaller than the size of the point here, okay? So we have much higher density of points, much higher precision. And with this new data and old one, we can look at the EMC effect and try to understand what's going on. There'll be many ideas trying to explain the EMC effect, but you can very coarsely divide those into 3 categories. One, do nuclear physics correctly. Okay, there's Fermi motion, there's binding. Neutrons are not a free Fermi gas. Take those things into account, and it will be fine, but don't change the internal structure of a bound nucleon. Keep the protonic physics as is, take care of the nuclear physics. And then there are 2 more exotic explanations that relate to different parts of the nuclear wave function and modification of the bound nuclear structure function. This is, again, a topic for a whole seminar, and it's been reviewed in this RMP we published a year ago with Jerry. But it's very well understood that taking care of your nuclear effects will explain some of the effect up to moderate X. It cannot explain the full effect. We're left with 2 hypotheses on the mean field type approach that Ian Chloe and Tony Thomas are promoting, and I'll not talk about that, and what we are doing with short-range correlations. And it's driven by the fact that we see this very nice linear correlation between the slope of the EMC effect and these coefficients, the scaling coefficients, Ix, telling us how many pairs there are in the nucleus. And we saw this in 2011, added a few nuclei in 2012. There was a lot of theoretical work on this, but experimentally we have not done any progress since we basically first highlighted the correlations. I'd like to show you that now we have actually experimental data that comes in. So the picture we get from the EMC SRC type correlation is that we can factorize a bound nucleus into a collection of quasi-free nucleons plus those that are in short-range pairs and those are modified. Again, it relates to a very different microscopical picture of what is happening in this region of the momentum density and the strong interactions, the short-range interactions that we have in this part of the momentum density. We can actually write it down mathematically, okay? So we can write the F2 structure function as a sum of these unmodified proton neutrons that are in this region and these modified nucleons, okay, that has, let's say, some F2n star that are sitting in this region, and how many of those we have is based on the number of pairs we have in the nucleus. So we write a nucleus as a sum of protons, neutrons, and modified nucleons that are in a correlated state. Now, the nice thing is that supposedly all of this has been previously measured, and we think that the difference between an unmodified and a correlated modified nucleon should be independent of the nucleus. Everything we see in short-range correlation indicates that there's a very strong interaction between nucleus of the pair, very weak influence by the A-2 system. So from helium-3 or deuteron all the way up to lead, I should not see any difference in this effect, in this pair. Okay, so what measured is actually not F2A, it's F2A over F2D, so let's write this down for the deuteron. But now I need to use this neutron, as many of you know, nobody really knows the free neutron structure function. So let's do it differently. Let's get the neutron as a function of the deuteron within the model, plug that in here, and calculate the ratio. I won't go through the math, I'll just give you the final expression. So this is F2A over F2D, what's been measured, as a function of a bunch of things we know, short-range scaling coefficients, which we know, N, Z, proton, deuteron, and this thing we want to extract. So the F2A over F2D, when you remove neutron, model-dependent neutron excess corrections, okay, it's called isoscalar correction. This is the actually measured ratio, okay? So F2 ratios for helium-3 all the way up to lead. I think the nuclear aerodynamics of this thing is very clear here, clear decreases here. And now, again, we factorize it into something that we know, SRC scaling factors. We take those from experiment. There's an isospin term that goes like P and Z, that we definitely know, and P over D, that P over D has been measured extensively, and something that I don't know what it is, but I hope it's universal, unlike this thing, which is not. It's very A-dependent. So let's do it. So I can solve this equation for this term, and I can write this thing I want to extract, the modified short-range nucleon structure function, as a function of things that have all been previously measured and are actually all A-dependent. So we have F2A over F2D, factors of Z and N running around, P, D, and short-range scaling coefficients.
Where did those come from? The NA and the measurements?
Those are the inclusive electron scattering measurements, the plateaus. Those are the plateaus in the inclusive cross-section pi x.
Okay, so what do you do for this? Measure the ratio.
Yeah, exactly. So that's why we construct ratios. So that's the only thing.
It's incorrect.
Huh?
This ratio they asked about. It's
No, nothing has isospin corrections to it. We do not use the free Newton structure function anymore. I don't trust it. I don't know.
for a two you do.
No, I don't.
Then okay, did you finish?
Nobody did. Starting from the forming paper to now, nobody uses isospin corrections for it.
No, but you said you assume that A2 is given by PNP.
Yeah, but I take here what goes in is the experimentally measured cross-section ratios without any multiplication by something that has to do with how many neutrons over protons you have in the nucleus.
Okay, it's hidden in another place. It's there. Of course it is.
I mean, if you show the first term, you have like Z minus N F2T over
Yeah,
D.
no.
This is an isospin correction.
This is, yeah, I said, there's an isospin term here, but this thing, the SLC scaling parameters, do not have any F2N or sigma N going to that. There's an isospin term here. I said that. That's clear. There's an N minus Z term clearly coming in that will give you a difference for the same A for N over Z here. Bottom line, this thing that is coming from all these very A-dependent quantities is universal. So we have one function to rule them all. If you want to explain this measured EMC data, all you need to know is this one universal function that within the normalization uncertainties of the data, these are all consistent with each other. Okay, one universal function, and you need to know how many modified SRC nucleons you have in the nucleus. So taking that with an amplitude that is the number of short-range pairs which you take from experiment, you get this, 1-to-1. The one clear universal function. And the thing that Jerry and Mark put up that is really interesting, this universal function is appears not only to hold in the EMC region, but it seems to also be universal in the higher X region, okay, with the amount of data we have there. And that also makes sense because the physics of the Fermi motion, anybody's calculation will show you, is proportional to the average kinetic energy carried by nucleons in the nucleus, and those are dominated by short-range pairs. Okay, they're very high momentum, they're about 60 to 70% of the kinetic energy carried by nucleons in the nucleus.
So, question is, isn't that just replotting the correlation between the strengths of the EMC effect and the strengths of the short-range correlation? Because in one case you have they depend both on the A, and now you put them together, and of course they have to, if they align on the figures, they have to show you something like that.
No, the way we relate this, so we can do a free neutron extraction, by the way, from this thing. The way we relate this, and I need to finish, so this is a good question. So what we can do with this is actually something different, okay? We can go back to the EMC-SRC correlation. We can now remove the model-dependent isoscalar corrections that have been applied to the EMC data that everybody's been working with. And we can use our universal correlation now to actually derive a model, okay, an actual calculation for the EMC-SRC correlation. And we do it for the correlation where you normalize the cross-section as a function of number of neutrons only, or when you normalize the inclusive cross-section as a function of the protons. And first of all, we see again that we do have a very good agreement between our model for the asymmetric nuclei. Before isoscalar correction, when we use our F2M in a self-consistent, still model-dependent way to apply neutron excess corrections, everything aligns on the n equals z line. That is now not a phenomenological fit parameter anymore. Now it is something we take from the universal function, and is not just a fit to the data. And we see also very nicely that the per-neutron EMC-SRC correlations saturate starting from carbon 12 and go for all nuclei basically from carbon all the way up to lead, which is fully consistent with this neutron saturating in quasi-elastic scattering to protons growing.
Yeah, that's where correction effects will be
done. That's the difference between this and this.
The difference of A to N or A to P.
Yeah.
You do explicitly connect A2.
Yes. Here it's A2N, which is normalized for neutrons and protons. Yeah. But I do not use for this quantity any free neutron structure function.
Oh, then
that I don't need to do. Moving from the top to the bottom, you do use a model-dependent neutron structure function. That's why we show both of them. So Jefferson Lab is back. So I've shown you all these results from data mining, but the lab has been working and has been performing better than ever. I've shown you the helium-3 experiment that took data literally less than 6 months ago. Paper is already being drafted, but there is more. I showed you the mirror nuclei. There are all sorts of studies we do of flight nuclei, adding a proton, removing a neutron, stuff like that, to really pin down an interaction. We're going to study this azospin dependence effect in a triplet of calcium-40, 48, and iron-54, from symmetric to very neutron-rich, back to heavier, almost symmetric. And there will be EMC measurements for those in short range, and we'll be able to understand the azospin dependence effects much better in this controlled triplet. And I'm not going to talk about it. Charles will talk about what we can do with tagged deep-in elastic scattering. But I'll tell you, this is one of the reasons I call JLR12 EAC phase 0 for the sake of this type of conferences, because we are studying EAC physics here. So we are doing this tagged deep-in elastic scattering measurement. We build a big neutron detector and installed it in Hall B of Jefferson Lab, and there's a proton detector. And we will be able to measure ratios of bound to free structure functions. And I'd just like to acknowledge the short-range collaboration. And I have the pretty face, so I travel around and talk, but these are the people who actually do the work, graduate students and postdocs, who are 100% responsible for all of this. Thank you.
So, questions? They were already on. Yeah, I guess I have to discuss discussing with you this afternoon. So what does this have to do with the EIC? And this is great stuff. But do you propose you want to go to higher Q squared, or you want to do what will
I want to do
EIC
tagging. I want to do tagging, yes. So I didn't talk about it because Charles will talk about it. I want to break down the dependence of the internal structure function on the nuclear interaction, on the overlap. I want to know if really when two nucleons become very close together, is that what really modifies the structure function or something else? Looking at the deuteron, what we're going to do is we're going to do deep inelastic scattering on, let's say, the proton, okay? And we're going to tag the deep inelastic scattering with a recoil neutron. So now by observing a low momentum recoil neutron compared to a higher momentum recoil neutron in a plane-wave approximation, I can tell you how strongly the world
You
interact,
can't
right?
do that, but you can do this at a fixed target experiment.
Yes, I can. Okay.
So,
the deuteron,
But to follow up this question, I mean, you started off saying that the EMC effect is still unexplained, but it seems that with this short range correlation, you make quite a lot of progress in this.
I need other people to say it. I agree with you, but I
Yeah. So in 5 years from now, and you mentioned there are new experiments, there's one dedicated EMC experiment. Is that a done thing?
I think this is the gold. Mark defined this as the gold-plated experiment. Okay.
Gold plated.
Yeah, gold.
Yeah, but I know I don't get the silver plated after when 20 years past from the moment.
No, the first one was approved.
But to solve the EMC effect, is there a measurement you need which
So
can
again,
only
I
be
think
done
this.
at the
I think this measurement. This is the level of how we're going to do things at JLab. So what you see here is for fixed X, our prediction for extracting the bound F2 over the free F2, okay? As a function of light density, we have two experiments, tagging a neutron, tagging a proton on the neutron, and this is how well we can do it. But this is, as always is the case between different machines, this is at the border. This is just at quasi-elastic kinematics, so W is exactly above 2, 1.8 if you trust bonus, and Q score is just above 2, and the statistics we coverage and the coverage, kinematic coverage we have is just at where we have to be. So I think we will be able to see things, hopefully, at JLab 12, and we will be able to do much better and quantify them and expand them and really get detailed enough level, not to show an effect, but to be able to give it to theoreticians to quantify and to constrain models and to relate it to GPDs and TMDs and all of that. For that, I think you will have to get an EIC. So there's seeing and there's quantifying. That's how I see it.
A very specific answer to the question is that what we know about the JLab and symmetry and definitely not much changes by probability is that for large X high twist effect already. Basically for X.5 and 2 square 4 or 5, it's half of the perception of high twist effect. So we need to go to much larger Q square to study fluid leading twist. It's interesting that high twist and
Cancel in the ratio,
kind of cancel, though it couldn't be exact. But basically, I give you an example. Basically, Fermi motion. Fermi motion just has different intercept in ratio. If you take leading twist, it's 1 minus x cubed, intercept at 0.5. If it is current situation, which is as overtly fitted to 1 minus x squared, then intercepted 2/3. So in this region, there should be some effects which
So I will try to address some of that question in my talk.
We agreed that I will just mention it and go away. So.
But just on this figure here, so there's another 12 GeV program specifically on the deuteron with the bonus detector, which can push the value of alpha S down to 1.1. Yeah. But the thing about, so alpha S of 1.2 basically means in the rest frame, you're probing a nucleon with around 200 MeV over C. So you're right on the edge of, you're right on the transition. Right. So you're doing a great job of the high momentum part, but you're not really doing a good job of the single body part.
Yeah.
And So bonus will push this down to
Yes,
about
bon-
1.1.
Bonus
The
will do
EIC
this, we will do this, and there's no
Well-
lot of in the between.
Bonus goes down to 1.1. The EIC can go down to 1.0. And a lot more that I will discuss.
Yeah, I think that the ANC can do things on a much wider space. So, it's like, what did we learn on E-prime P scattering from BKF to JLab?
But it's just
doing it better.
how to play it, devil's advocate. Okay, but
It's fun.
it's a qualitative improvement, quantitative improvements you expect. There is not a qualitative step which brings you this.
I don't think I agree with that, because I think with this data, I don't think you will be immediately capable of taking that and go to models of GPDs and things like that and immediately put tight constraints on them. I think if you have this over a wide phase space in very high Q square, like Mark said, where you don't need to worry in the theory about higher order, leading twist effects, stuff like that, I think those would be easier to compare. What we see, which is very odd, by the way, is that the JLab data on the EMCA didn't show, the light nuclear data. There was no done independent elastic kinematics, okay? They measured W squared greater than 2, okay? Which means they were 100% measuring resonances, okay, all throughout the data. Still, the cross-section ratios match slack, okay? So there are, like, definitely, I mean, they're measuring, it's a duality type thing, they're measuring resonances, but when they take the ratios to the neutron, they get cross-section ratios which match slack data. And it's very hard to find in the paper. It's like a figure caption saying where the W square cut is, and it's a big mistake of W squared greater than 2, and you see W and 2, and you think everything is good. We did, of course, W greater than 2 and all of that, but it's very borderline kinematics. So we'll be able to see things, I think, to really connect it to hardcore QCD. Lattice calculations, for example, of this universal modification function, all those things, I think those will have to come with the ASIC.
Yeah, let me say the thing. Maybe one of the wrong impressions that is given by this talk is because you present your model. The main issue with the EMC effect has never been to describe the EMC effect. There was always plenty of people who to describe the EMC effect. The main issue has always been that there are many descriptions of the EMC effect, and even here, I'm not sure if that includes everything that is still on the market. And one of the problems with the figure you showed at the end is there was already some people that tried to describe this in class, and the points are just not following any trends like the predictions. And so that can be linked to all the issues that have been discussed about higher twist. But clearly there is no guarantee that the points will exactly go line up on one of the options. And if you look at the error bars that you actually put on this figure, if things are not lying exactly on one of the predictions with those size of error bars, it would be very difficult to say between the different models. It's not like it's going to give a sharp answer right now.
So two things.
And just let me finish, because I seen you plugged in your experiment and Charles plugged in his, so I don't see any reason not to plug in mine. We have a third experiment that will do those kind of measurements, trying to do the connection between the two, both having low energy and a little bit of high energy. And also, one point that we try to highlight is that all of this is on deuterium. And I think if we want to have really a universal answer for these things, we need to be able to go to higher nuclei. So we're going to try to go with helium-4. But I mean, the EMC effect is an effect that we see in nuclei by comparison to deuterium. So going to look for the EMC effect in deuterium is always a little bit peculiar if you want to make an explanation that works.
So I'll comment on three things. One, everybody can.
First, what is your experiment?
The alert program.
It's the same as us, only lower momentum tagging and bounce
It's also
systems.
tagging on helium-4.
In deuterium and helium-4. And we do ratios of the two, so it's tagging on both sides of the.
No, the main problem is tagging. Why I posted down.
Let me give him a chance to answer, and then we have to also.
Yeah, so first of all, there has always been many models to the EMC effect. That's a wrong claim these days, okay? there has been many models for the EMC effect. Everybody's model was cool, everything was nice, but then theoreticians told us what to measure. There were Delian measurements, right? There were many other measurements done. And these days, there are not many models for the EMC effect on the market.
So
actually.
where do you put X-ray scaling in this?
X-ray scaling is ruled out. because you
Exactly.
cannot
It's not a valid
explain
model.
the EMC effect and the Drolian data.
It's just not a valid model anymore, even though people still compare to it. It's not a valid model.
There's a curve that's in the Drolian experimental paper shows rescaling works, but if you take that exact version of the rescaling, it no longer fits the EMC effect.
You can't fit both Delian and the EMC effect together with this model. So if you try to fit everything together, there are actually two families of models, okay, which are these two. And there are variations of these families of models. There's very beautiful work that Jan Wei, Achim Schwenk, and Will Detmond did in EFT, which is equivalent to what we do here, and Petty and Kulagi and Petty do work, and that goes in here, and obviously point by configuration suppression, which goes in here. So there are variations of these models, for sure. But there are actually two large families of models that are capable of explaining all the data self-consistently there. So this impression that everybody's model is cool, I just simply disagree with. That was the first point. The second point was about the reach of the experiment. Well, we have two experiments that are covering quite a big reach, especially this one, which is the better one, but we'll run later. These uncertainties over this range are amazing. Now, I don't need them to follow a line. It would be boring and I'd be very sad if they follow one of these lines, okay? My own personal hype about physics when they don't follow a line. But the issue with previous measurement that did this type of measurement was not that they didn't follow a theory line, so we didn't know what to do with them. Who cares about theory lines? I couldn't care less. Was that they were in kinematics dominated by reaction mechanism effects, okay? And there are calculations by Nisak and others that have shown that, and they've shown where to go to reduce these effects. And what we're measuring here with the band detector, we're going to 160 to 170 degrees, where we compared 5 different models coming from very different groups that always disagree. And in this picture, this region, they agree. We have the central neutron detector that measures in regions where finite state interactions are large. I didn't want to go into all that, but we are doing measurements over a wide phase space where reaction mechanisms are large, where they're supposed to be small, so we can do corrections for the residual, and there's a lot more going on
I
here.
agree, that's not my
So,
Okay, we have to.
so there's no problem with the accuracy of this
We
data.
have to stop now because we have this afternoon discussion session, where we can bring this all up. And there will be cookies. And there will be cookies. So we have a sugar rush. We are even more excited about it. Ciao. You're next.
You want this thing?